Okay, we are now recording. As I was saying, I have looked at many of the homework assignments that you've submitted, not all of them, and I saw pretty much the same things that I see every year. Most of you are really good about doing graphs. You know how to do them properly, shall we say. Uh, but a few of you, some of your graphs, let's just say there was room for improvement. And I am not going to show your actual graphs because I don't want to embarrass anyone. I'm going to just kind of make up a few graphs here. Let me open up my whiteboard here and get rid of that. All right, so I'm going to draw some things that are similar to what some of you submitted. All right, so let's suppose this is the page. All right, and so some of you had the graph. So here's your x-axis, here's your y-axis, and your data looked like that. So what do you guys think about that? Somebody unmute yourself and tell me what's your impression about this kind of a graph? What is a potential problem that you see with it?
Um, can you hear me?
Yeah, I can hear you.
Okay. So I feel like those points, they're a little big and they're not exactly dots, so you can't really tell if they were lined up on some sort of line, if they're on one line or a line like right next to it. It's not exactly accurate. And there's no um like notches to show how much of anything that there is on the axes.
Okay. All right, very good. So yeah, we definitely need tick marks on our graph, that's for sure. And the graphs that I got, they actually did have tick marks. But what you said right now is really important. The reason that we're graphing these things is because we want to answer the question of whether it's linear or nonlinear. So when we have all the data grouped right here in a tiny part of the page, and we got all this wasted space right here, whoops, okay, all right, all that wasted space, it makes it really hard for us to answer the question with confidence. Now, yeah, maybe we could kind of draw a line through there, but they're grouped together so tightly that we really can't say with confidence whether it's linear or nonlinear. So it's very important that we fill the page as much as possible. You know, you want to set your settings, set your axes, min and max, to try and fill the page as much as you possibly can. That's really important. So in the future, please try to do that. Another thing that some people did that I wish you had done differently is they didn't label their axes. Now they did put numbers here. All right, so this is 10 and this is 20 and this is 30 and 40 and so forth and so on. But they didn't tell me 10 or 20 what. So I don't know if the numbers on the x-axis are meters or seconds or shoe size or what. I have no idea. You gotta label the axis. You know, if it's length, tell me its length. And same thing with the y-axis. Okay, whatever units it is, tell me what units it are. That's really important. A few of you got your independent variables and your dependent variables mixed up. So the x-axis always has to be the independent variable. Let's see, independent. Okay. And then the dependent variable has to go up here. That DEP stands for dependent, right? That's really, really important. And a few of you got that mixed up. So when you go to analyze the results and try and find the equation, which by the way is what we're going to do today, if you got your axes swapped, that's going to be a huge problem. Some of you did something that I thought was really good. So let's say here's your x-axis here. Let's say this is 10. So you did an experiment where your independent variable was set for 10, and then you got some number there. And then you did it again, and you got a slightly different number, which happens in the real world. That happens all the time. Whenever you're measuring something, or whenever you've got something that's subject to random variations, if you repeat an experiment, you're probably not going to get exactly the same answer every time. All right. So what you did was you plotted all of your data points, which was great. I love that. Okay. So let's say our data looks like this. All right. So now we can start to say with a lot more confidence whether it's linear or nonlinear. Now, if you just look at the first three lines there, or the first three groupings, okay, you look at it and say, yeah, hey, wow, that looks pretty linear. We can fit a line through there. Now, there is some ambiguity as to what the slope of that line is and what the offset is. But if we just look at those first three there, we can fit a line through there pretty well. Oh, but that last group, okay, that's a problem. We can't fit a line through. So the lines that we fit through that first group, we can't fit them through that second group, or that last group. So if you plot all of the data points like that, that helps you know with a lot more confidence what's going on. So like let's suppose that these guys here weren't there. So let's suppose that all we have is those three data points, or those three groupings, all right? So it looks like it's linear, and we can say with reasonable confidence that it's linear. Now, if I were to ask you to come up with the equation of the line, okay, then there's going to be some wiggle room, because as you can see here, there are two lines, and both of those lines go through all of the groupings. Okay, so there's a little bit of ambiguity here, but that's important to know, because if we just had one data point, if instead of graphing all 3 points, if we had just graphed the average only, so just imagine that there's only one data point right there. Okay, so we would come up with a line, and we would say, yes, it's a line, and here's the equation. We wouldn't realize that there's actually some uncertainty. By graphing all three of the data points, that gives us an idea of what the uncertainty is. And that's really important. In physics, you always have to recognize that whenever you measure something, there's going to be some uncertainty, and you need to have an idea of how much uncertainty there is. So we're going to do multiple runs. And we're going to, tonight in our homework, we're going to redo the first lab, except I'm not going to have you do the same ones you did before. I'm going to have you do a different lab. But we're going to basically redo what we did last time, but we're going to do it more carefully this time. And also this time, I'm going to allow you to graph it using Desmos, because, hey, I agree with you. Graphing stuff by hands is ridiculous, especially when we all know how great Desmos is. So by all means, let's use it. But it was good for me to see how you guys graph things by hand. It gives me an idea of where you're currently at, and that's important for me to know. Okay, a few of you, you had your hypothesis, and then you graphed your data, and then you told me whether your hypothesis was right or not. And I could see that you're still having trouble with understanding what direct versus inverse means. All right, so this graph right here, I want you guys to tell me, is that a direct relationship, or is that an inverse relationship?
Direct.
In fact, maybe you could just type it into the chat box there. Let's take a little poll in the chat box here. How many think that's direct? How many think it's inverse? Okay, looks like everybody's agreeing it's direct. Okay, good. All right, so that means you can stop now, thanks. So as our independent variable gets bigger, so does our dependent variable, so that is a direct relationship. Now, if the data look like this, that's still direct, it's just direct and nonlinear. Now, it also might look like this, okay? Again, it's still a direct relationship, okay? It's just direct and nonlinear, okay? So some people, that when they graphed their data, it looked like that, and they claimed that that was a direct relationship. It's actually not. That's an inverse relationship. So you got to be careful. Now, inverse relationships might be linear relationships like that. They might be nonlinear ones that look like this, where it's steep at first and then it shallows out at the end. Or it might be shallow at first and then it steepens up at the end. All of those are inverse relationships. Okay, there's just some are linear, some are not. Okay, Eliza. All right, see you later. Um, all right. And what other notes did I have here? I think we'll call that good. Okay. And some of you did not tell me what your hypothesis was. So please in the future, try to do that. That's important. All right. So I'm going to stop sharing of that. And let me quickly open up Canvas so you can see what we're going to do today. Okay. Good. So now let me start sharing that. All right. So here is my Canvas page. Should look similar to yours. Let me click on the physics page. And the assignments. So one of the assignments, which was due today, was reading the syllabus and confirming that you've done so. And when I look on Canvas, I see that most of you have done that, so good for you. But a few of you still haven't done that. So do that, that's really important. It counts as an assignment, it's worth 10 points. And if you didn't do it by the beginning of class today, well, that's going to be one of your late assignments. Remember, so when you read the syllabus, hopefully you understood that I allow 2 late assignments per term, and I'll give you full credit for them because I realize, you know, life happens. Sometimes you don't get stuff in on time for some very valid reason. So I do allow 2 assignments and full credit, but after that, I don't take late assignments anymore. So if you didn't turn in the syllabus/disclosure on time, you've already used up one of your 2 late assignments. Be careful with that. All right, so you have probably noticed that there is a recording of the first day's class on there. I record all 3 classes, but I don't put all 3 of them online. There's no point in doing that. I just pick one of them and put one of them online. The first physics lab, that's the one we just talked about, and I think you guys got that pretty well. Before I move on, does anybody have any questions? Did any of you have any problems or anything you wanted to discuss about that first physics lab before I move on? I'm not seeing anything. Now my chat box, when I share my screen, my chat box disappears and I can't get it to come back. Let me stop sharing for a second. Okay, so I'm not seeing anything in the chat box and I'm not hearing anything. Can I safely assume that means that you don't have any questions? That's what I'm going to assume unless you say otherwise. All right. So don't worry about this flat Earth assignment. That one won't show up on your Canvas yet because I haven't published it yet. But that will be the next assignment that we do next week. All right, this is our assignment for tonight, our first physics lab, but this time we're going to do it a better way. All right, so here is what it looks like. We're going to go back and we're going to look at the pendulum lab. We're going to redo the pendulum lab. Oh, wait a minute. Oh, my goodness. We need to talk about the results of the lab. I haven't done that yet. Okay, so let me stop sharing this. I need you guys to tell me what your results look like. So let's start with the Cannon lab. That was the first one. Can someone who did the Cannon lab please share with us what your results were? If you have your graph with you on paper, I'd like you to hold it up and show us your graph, or if you want, I can enable screen sharing so that you can do it that way. But somebody who did the Cannon lab, I want you to come on and tell us what was your hypothesis and what were your results.
Yes, my hypothesis was the first was that it wasn't going to be direct or inverse. It was going to be something else.
Okay, hang on just a sec. Before I go on further, you guys know that in the upper right hand, you got 2 options. One option is what we call speaker view, and the other option is what they call gallery view. Let me recommend that everybody go to speaker view. That way, when you do that, then when Dylan talks, you will see him nice and big and everybody else small. That'll make it a lot easier for us to see his graph. Okay, so Dylan, go ahead and continue.
Yeah, so for my first part of the hypothesis, I chose something else because looking at the Canon, if it went straight up, then it would be 0, or straight down, it would be 0. But then in between, it wouldn't be. And so it was gonna, as you increase the angle, like go up and then down once you got up to 90.
Do you have your graph that you can show us?
And then my second part of the hypothesis was I said something else, but I kind of meant nonlinear. I just since it wasn't going to be a straight line.
All right, so you guys can see that it is clearly a direct relationship at first, but then after a while, it starts going and being an inverse relationship, and there's clearly a maximum there. But now, Dylan, you said that at 0, the distance would be 0, but when I look at your graph there, I see that at 0, the distance is most definitely not 0. So what's going on?
I meant negative 90 and 90. I just, in my head, thought 0 and 180 instead of those.
Okay. All right. So I see a maximum there. Can you kind of estimate at what angle you get the maximum?
Probably around 40 degrees.
Now, most people would say that they would expect the maximum to be at 45. And yet, in your case, it's clearly less than 45. Can you think of any reason why it's not 45?
Let's see.
Can anybody else chime in with the reason? What most people, if you ask them what angle would give you the maximum distance, most people immediately reply 45 degrees. But if you look at Dylan's data there, it clearly is not 45. It's a lower angle. Why is that?
Would it be because when you shoot it at a lower angle, it has more power going out and it's not going up as much? So I don't know.
Interesting idea. Anybody else want to chime in with something?
I'd like to add on to that and say that because of the extra power and it's starting 10 meters up, it results in it going farther rather than losing, or not losing energy. There was no energy. I'm sorry. yeah, 10 meters and extra power.
There is definitely energy. Yeah. Ethan has really hit it right there. It's because it's up on a raised platform. If the cannon was down at ground level, you would find that 45 degrees is in fact the angle that would give you the maximum. But when you're up on a hill there, that changes things. Kind of an interesting little twist there. Okay, thank you guys, and thank you, Dylan. I appreciate that very much. Now, how about the next group? I believe the next one was the mass on the spring. Can somebody who did the mass on the spring share your results with us? Come on, somebody speak up here. So mass on a spring, who would that be? So Aubrey or Zane, Kennedy, maybe you? Nobody wants to speak up? All right, tell you what, we'll come back to you guys. How about the next one, the mass on the pendulum? Somebody who did that one, please speak up and tell us what your results were.
I can do that.
Okay, great.
Okay, so my hypothesis was that as the mass on the end of the string increased, the period would decrease. And this is my graph. So the period stayed the same regardless of the mass at 20 degrees. And it took about 1.6 seconds.
Very interesting. All right, so Max's hypothesis was similar to what most people think. Most people think that when you change the amount of mass there, it's going to change the period, but it looks like that's not the case. Looks like no matter what mass he chose, he got the same period. All right, so what do we say about the relationship then? Direct inverse or what?
No relationship.
No relationship whatsoever. And that happens a lot. And I did this on purpose because I wanted you to recognize it happens a lot. There are times when there's no relationship. So you can make that mass be anything you want and doesn't affect the period at all. Now, what about the linear versus nonlinear? It's, what do you think there, Max?
Well, it is a line. You could graph it as a line, but is it linear?
Okay, you guys agree? I mean, if you look at the graph, it clearly is a horizontal line. So technically, I guess you could say it's linear, but in reality, the question doesn't really apply. Because if there's no relationship, then you really shouldn't label it as linear or nonlinear. The correct way to respond is that there's no relationship. But if somebody wants to be really nitpicky, they say, well, a horizontal line is a line. Yeah. Okay. Next group. What is that? That's the wave on the string. We got the oscillator and the little wave going. Somebody want to speak up who did that experiment? Well, you guys are a quiet group. Yesterday's classes just kept on going.
I think I can speak about it.
All right, good for you, crew. And can you turn on your camera?
Yeah, let me grab my graph first.
Now, if you have it on your computer and you want me to enable screen sharing for you, I can do that.
I don't need screen sharing. I have a physical version of it. So, can you see my graph very well?
Yeah, we can see it.
So, yeah, it looks like.
So first tell us, what was your hypothesis?
So my hypothesis was that the relationship would be inverse and nonlinear because I know that as the frequency is getting smaller, then the wavelength will get larger at like increasing pace.
Okay, so that's an inverse, but what made you think it was going to be nonlinear?
Just because like when I was thinking about like how waves work, if you get to like 0, then the wavelength is infinite. So it has to be nonlinear because there would be no way to get that and then have it go slowly. Sorry, maybe I'm speaking weird. But I knew that as the frequency was increasing, like it just wouldn't change it as much as you got further down. I don't know.
All right, I like what you're saying. There's another way to think about it that makes it very clear. It obviously has to be nonlinear. And the reason that you can be absolutely certain that it's nonlinear is because when we did the experiment, we saw that as we increased the frequency, the wavelength got smaller, right? So we know that our graph is going to start off heading downward. But we also know that there's no way that the wavelength could ever get below 0. It's impossible to have a negative wavelength. So there's a lower limit. Therefore, if you know that the thing starts off heading downward, but you also know that there's a lower limit that it cannot possibly get below, well, then obviously it has to be nonlinear. Because if it were linear, if it starts off heading downward, it's going to keep on going downward and it's going to hit 0 and it's going to go negative. So obviously cannot possibly be linear. All right, can you show us the results just one more time?
Yeah.
All right, very good. All right, thank you for that. All right, now our last group was the laser refraction, where we're shining a laser at the water and the light ray gets bent. Somebody from that group speak up.
I guess I will.
Thank you.
Whoa, wait a second. Hey, what's up?
Hello.
Anyway, so my hypothesis was, well, we already covered this, that the relationship is going to be direct. Anyways, and then for the linear, non-linear, at first I said linear because I just thought it would be. This is my graph.
All right.
And yeah, I think it's nonlinear because it begins to curve. Yeah.
Pretty clearly nonlinear there, yeah. Now this is one that most of you have not really played much with lasers, so you really couldn't have made an educated guess about the linear versus nonlinear. So she just made an uneducated guess. So it turns out she was wrong. So does that mean I should take off points for your hypothesis being wrong?
No.
Yes.
Oh, rats, you're no fun. So, okay, all right, I won't take off any points. All right, and it's important. You guys need to realize that quite often that's going to happen. Your hypothesis is going to turn out to be wrong. That's okay. The important thing is to have a hypothesis. All right, very good. I like your data a lot there. Okay, now let's jump ahead and talk about today's assignment. Today, we're going to redo the lab, except you're not going to do the same lab that you did before. Or at least, let me rephrase that. Everybody this time is going to do the pendulum lab, but the independent variable is not going to be the mass this time, because as Max showed us, if the independent variable is the mass, turns out that's pretty boring, because changing the mass doesn't affect the period, right? So just to be sure there, let's get this thing going, all right? And I'm going to change the mass. So there's a tiny mass, and I didn't see the period change. There's a really big mass. Yep. It looks like changing the mass does not change the period at all. So that's boring. Therefore, we're not going to do that. All right. So here's what I want you guys to do. For your homework tonight, the independent variable is going to be the length of the pendulum, the length of the string. Now your dependent variable is going to be just what it was before. If you come down in the lower left here, you see there's the stopwatch. So I'm going to click on stopwatch. All right, bring it up here. All right, so we're going to measure the period, but our independent variable is going to be the length. And by the way, when we graph it this time, we're not going to graph it by hand. We're going to graph it using Desmos. And we're also going to do one thing that I didn't ask you to do last time. We are going to find the equation that fits it the best. All right, now I'm going to start off, I'm just going to do a little bit here to make sure that everybody knows what to do, but I'm not going to do the whole thing for you. Where's the fun in that? Let's make the length be the smallest possible. So 0.1, holy cow, look at that. Wow, that definitely changed the period, didn't it? So if the number is small, if the length is small, then that means that the period is also small. If we make the length bigger, okay, it's clearly the period is bigger, and then let's make it be as big as possible. Okay, great. All right, so what does that mean about the relationship between our independent and dependent variables? Is that a direct relationship or is that an inverse relationship? I want everybody to type into the chat box here. Tell me whether that's a direct relationship or an inverse relationship. And I want everybody to type something in the chat box. Oh, wow, this is interesting. About half of you are saying it's direct and about half of you are saying it's inverse. Okay, this worries me. This, it should have been clear from last night's homework. So let's go and look at it again. So I'm going to make my independent variable small, right? Whoa, that's interesting. I've never seen it do that before. Let's try that again. Okay, that's funny. Oh, I like that. Hang on a second here. I've got a bunch of windows that you guys can't see. Let me, all right. Okay, so let's make it really small. Come on. All right, pull it back a little bit. All right. All right, so when the independent variable is small, then the period is small. Now, don't get the word period confused with the word speed. I mean, it looks like it's moving really fast there, which, by the way, is questionable anyway. But the amount of time it takes to go and come back is very small. So if the independent variable is small, the dependent variable is small. Now let's make the independent variable bigger. Now you see that the period is now much bigger. So clearly, I would hope that you guys all understand this is a direct relationship, not an inverse relationship, okay? If it was an inverse relationship, then the period would get smaller as the length got bigger. So everybody hopefully okay with that. All right, so we know now for sure that it is a direct relationship. The question that we need to answer for tonight's homework is it linear or is it nonlinear? And and I also want you to come up with the equation. So if it's a line, I want to know the equation of that line. If it's a nonlinear function, I want to know what is the function. Let's take a couple examples here. I'm going to start off really small, and I'm going to measure the period just like you guys do. Now remember, there's always some human error. When I click on the start button and I click on the stop button, I can't get it timed exactly right. So there's going to be some error. So what we're going to do is we're going to do 10 repeats, and then we'll divide what the time we get divided by 10. All right, so here goes start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so it looks like the period is 0.657, because remember, I'm going to divide this by 10. All right, now I want to graph this, but I'm going to use Desmos this time. All right, I'm trusting you guys know how to use Desmos. Everybody in the 8A class, they all told me, yeah, we know Desmos, we use it all the time. So I'm trusting that's the same with you. So I'm going to open up a new window here. I'm going to go to desmos.com. You can see it automatically filled it in. So clearly I go to Desmos a lot here. You guys should too. It's wonderful. If you don't already have a Desmos account, please sign up for a Desmos account. In my case, I already do. All right, so it's going to take me to here. They've changed their opening screen a little bit. If you haven't used Desmos in a long time, you'll see it's slightly different. So I'm going to click on Math Tools and go to Graphing Calculator. And so now, okay, now we are in the screen that should be familiar to all of you. In fact, tell you what, let's just take a poll. I'm going to ask you a yes/no question. I'm going to say, are you guys comfortable with using Desmos? And I want you to type into the chat box either yes or no. Yes, where you're really comfortable, you've used it a lot, or no, if you haven't used Desmos much, if any. I'm seeing a whole lot of yeses and a yeah. Okay, good. All right. So you guys then know what I'm about to do. I want to plot the data. So I'm going to get a whole bunch of data from this experiment. I want to plot the data points. Therefore, hopefully you know that what I'm going to do is I'm going to click on the plus sign over here, and I want to enter a table. The default names are X1, Y1. We can change those if we want, but I like them, so I'm going to stick with them. What is my X1 value? Okay, somebody type into the chat box. What number should I type in for X1? Remember, X is my independent variable. So let's come back to here. What is the value? Okay, very good. So 0.1, all right? My independent variable here is 0.1. And my dependent variable is the period, which not 6.57. Remember, that's for 10. I have to divide that by 10. So 0.657. 0.657. All right. Now, I want every independent variable setting to be repeated 3 times. So I'm not going to just jump up to the next one. I'm going to redo this one. So let me clear the clock and start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Hey, I got a different number this time. Welcome to the real world. That's the way the real world works. All right. So 0.659 is what I got this time, which is actually pretty close. All right, and one more time, just for good luck here. Actually, not good luck, is because as I'm requiring it. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, 0.651. So my independent variable is still 0.1. My dependent variable is 0.651. All right, now I can go and do my next one. I'm not going to do it for you because this is your job to do this. I'm just going to do an example here. I want you guys to go up in increments of 0.1. All right, so we did 0.1. So if we add 0.1 to that, we get 0.2. and you'll see the period has gone down. So I want you to do 3 repeats here. And then we're going to do 0.3 up here. You can see what it is. And then we're going to do 0.4 and then 0.5 and so forth and so on all the way until we get to 1. And then we're going to graph that data. So I don't want to actually do the experiment for you. Let me just make up some numbers. You can't do this, but I'm the teacher. I can get away with things that you can't do. All right, let's say that point, and also I'm gonna do fewer numbers. I want you to do 0.1, 0.2, 0.3, 0.4, but because I don't want to waste everybody's time here, I'm gonna skip to 0.5, and I'm just gonna make up a number. Let's suppose that the period that I get is 3.5 seconds, and when I repeat it the second time, I get 3.4 seconds. And when I do it a third time, I get 3.57 seconds. All right. And again, I want you to do 0.6, 0.7, 0.8, but I'm going to skip. I'm going to go all the way to 1. And I'm just making up numbers here, which you cannot do. I'm going to say when we get to 1, let's say I got, maybe 5.8. And when I repeated it, I got 5.9. And when I repeated it the last time, I got 5.75. Okay. And then you, of course, will have more data points on yours. Now, here's my graph. And we have exactly the problem that I saw from some of your guys' data. Most of the graph here is empty. Look at all this wasted space over on the left, over on the right here is just totally wasted. So I cannot say with confidence whether it's linear or nonlinear. Now you guys hopefully know that you can move the graph around by clicking on it here, but I want to zoom. So if I click the plus, then yeah, it zooms in, but it zooms in too much. It doesn't zoom the way I want it to zoom. So if only there was some way to get it to expand the X and the Y axis independently. Well, it turns out there is. Now, if you have a touchscreen computer, then it's really easy for you. Let me move. I've got a window here that you guys can't see that's kind of messing things up for me here. Okay. All right. If you have a touchscreen computer, you can take 2 fingers, and if you touch these 2 fingers on the X-axis, well, actually, if you just touch anywhere on the screen, okay, it goes bigger and smaller like that. But if you touch on the X-axis, you can expand only the X-axis. That's a pretty sweet little tool there. And we can do the same thing on the Y if we want. In this case, we don't really need to, but in fact, don't want to. All right, so I've expanded my Y-axis, and there's my X-axis. All right, now, whoops, and one thing you got to be careful of is if you move the mouse, it wants to move the whole thing there. All right, so if you got a touch screen, wonderful. What if you don't have a touch screen? How are you going to change the axes there if you don't have a touch screen? Well, hopefully you guys already know the answer to that. Over here on the right, so if that little window with everybody's faces is over on the right side of your screen, click on the top and slide it out of the way so that you can see what I'm pointing to here. There's a little wrench right here, and then the plus and the minus sign. So let's click on the wrench. And that opens up a couple options here. If we look on the X-axis, we'll see some numbers. That allows, we can type in here whatever numbers we want. All right, so let's say we want to start at 0, and we want to go up to 5, which is not the best setting in this case, but right. All right, and when we click here, there you see, so it has gone now from 0 to 5, exactly what we told it to, but as you can see here, 5 is not the appropriate one. It would have been better if we typed in, like, say 1.5. So let's go back and let's fix that. Now the reason it changes is because I manually moved it. All right, so we want our maximum there to be 1.5. All right, very good. So see, it's possible to, but it's much easier if you got a touch screen. And by the way, I know a lot of you guys have Desmos app on your, have the Desmos app on your phone, and your phones are certainly touch screen. So here's a case where doing it on your phone might be easier than doing it on the computer. All right, now I want to know, is this a linear relationship or is it nonlinear? What do you guys think? Let's see, let's turn on annotation here. So if I were to draw a line, that's not a very good line, but all right, I can make that line go for the first 2 points, or I could make it go through the second 2, well, groups, I shouldn't call them points, I should call them groups, right? But I cannot get a line that fits through all of the groups. So I can say with very high confidence, this graph is definitely not a linear function. All right, but you guys know that Desmos can come up with equations for you. So let's suppose that it did turn out to be a linear function, and I want to know what the equation is of the line that fits this data the best. Do you guys know how to use Desmos to find the equation? Which, by the way, is a term that's called doing a regression. Have you heard your math teacher talk about doing regressions? All right. Anybody know how to get Desmos to tell us the equation of the line that fits this the best? No? Okay, well, hey, you're going to learn something. All right, here's how you do it. You come back here. Oh, let me turn off my annotation here. All right, so I'm going to come back to the plus sign. I'm going to click on plus sign, but this time I don't want a table. This time I want an expression. So I'm going to come down to f of x expression function, in other words, right? And let's say that I think it's a line. So I'm going to ask Desmos to tell me the equation of the line that fits the best. Well, what's the generic equation for a line? It's y equals mx plus b. All right, now I've typed that in there, but Desmos doesn't really know what to do with it. Now, if I had put numbers there, if I had said that a b value, let's say, is 2, and my m value here was 0.7, okay, yeah, Desmos knows what to do with that, all right? But that's not what I want. I want Desmos to tell me what is, oh, okay, there we go. I want Desmos to tell me what is the value of m. So I just type in a generic m and I type in a generic b, but Desmos doesn't know what to do with it. Here's the trick, which hopefully you guys saw this from your math class, but okay, maybe it's new for you. Instead of putting an equals sign, I'm going to put that little squiggle line that's called a tilde, and every computer has it in a slightly different place. So you got to look on your keyboard to find out where it is on your computer, or you can use the keyboard here to get it. But anyway, so y, and then I use that little tilde, mx plus b. But I don't want just any old y. I want the y's from this table right here. And you can see that these y's, they're all given the name y1. So I want this to be y1, and then tilde, m times, and it doesn't, don't want just any old x, I want x1. So I make it x1. Bingo, there we are. Okay, once I tell it that, now Desmos can handle it. All right, Desmos is saying that the m value that makes this line that you're seeing right here, which is the line that fits the data the best, that m value is 5.69. And then the b value that makes it fit the best is 0.286 and change, right? Yeah, so if you guys didn't know that, I need to have a talk with your math teachers. This is something you guys should all know. All right, so this is the line that fits it the best, but I'm not happy with it. And if we zoom in here, right, you can see that the grouping of the points that are in the middle here, they're all above the line. And then the ones on the right side, they're all below the line. And the ones on the left side over here, they're all below the line too. So that tells me that this is not really a linear function. All right, so I need a function that starts off pretty steep. In fact, let me go back to annotation here, and let me just make that a little, oops, that wasn't what I wanted to do. Try this again. All right, I need a function that starts off kind of steep and then gets a little bit less steep as time goes on. Anybody got a suggestion of a function that would do that for me? I can hear somebody trying to talk, but I'm not able to hear what you're saying. You can type it into the box there if you want. Come on, somebody tell me, what's a function that starts off steep and then, okay, logarithms work, okay? So it could be logarithmic. Any others? How about a square root function? Let's do a square root function, all right? So I'm going to, let me stop my annotation. Okay, I'm going to, I want to keep the line there, but I just want to not show it. So you guys know that you can click on this little icon over here. So the equation is still there in Desmos's storage section. It just doesn't graph it. All right, I'm going to click on the plus sign. I'm going to add in a new expression. So my guess is that maybe it's a square root function. So let's try that. So let's do y1 and then this little tilde. Now there might be, so I'm going to put a square root of x1 here, but there might be a value in front of that square root, you know, kind of like the m value. So I'm going to just call it a. You can call it whatever letter you want. And now square root. My goodness, I've forgotten the words for square root. If only there was a place I could look that would find it. Well, let's try this keyboard. Hey, looky there. Okay, there's a square root function right there. So let's click that and then make the keyboard go away. All right, so a times the square root of, now my independent variable is x1, so I'm going to say x1. Okay, all right, okay, there we go. And there might be an offset here. As you can see, the data doesn't fit super well. There might be an offset, so I want to do a plus b, but I don't want the plus b to be in the under the square root. So I have to hit tab to get out of the square root. And now I'm going to do a plus b. All right. Oh, hey, that looks pretty good. I'm liking that. So the equation then, if we go with the square root function, the equation that fits it the best is y equals 7.53 times the square root of x minus 1.75. All right, is this cool or what? Did you guys know that Desmos could do this? All right. Therefore, now when you guys do the homework tonight, okay, remember everybody's going to do the same lab. So you're going to do the pendulum lab. Your independent variable is going to be the length. Don't mess with anything else. Don't change the mass. Although in this case, we found out actually changing the mass isn't going to affect anything, but just as a general rule, you want to hold everything else constant. Only change the one variable that you're interested in. Therefore, let's keep the mass the same. And let's see, what other things might you be tempted to play? Oh, the gravity. Oh, isn't this cool? Look at this. We can do this on different planets. All right, so take a look at what it's doing on the Earth. If we go to the moon, wow, that changed things big time. All right, what if we go to Jupiter? Whoa, yeah. Okay, so clearly changing the gravity here makes a big difference. Therefore, let's not mess with gravity. Okay, so your independent variable is the length of the string. Your dependent variable is the period, which, as you hopefully all remember, is the time it takes to go one side and back. You're going to use Desmos to graph it, and you're going to need to send the graph to me. Do you guys know how to send graphs to people? I mean, hopefully your math teacher certainly should have covered this, but just in case your math teacher didn't, let me tell you. You see this icon that I'm pointing at up in the upper right here that says share graph? That's what I want you to use in order to send me a copy of your graph. So let's click on the share graph icon. And what we get here is a couple of ways we can share it. One way is it gives us a link, and we could just copy that link and you could paste that link into a message that you send to me, and that would work. It's not the way I want you to do it this time, just because I want you to know how to do it the other way, because there will be times when this other way will be a better way. The other way that I want you to do it is export image. So click on that, and it gives you a couple options here. You can do it with a thin line, a medium line, or a thick line. I don't care which one. Personally, I like thin myself, but hey, whatever you want. And then you can download it as a PNG file. Now, they do have a beta here where you could download it as an SVG file, but That's only in beta, and I don't like it anyway. I like PNG files. Therefore, please download it as a PNG file. So if you click on this icon, on that icon there, now you should be able to see down in the bottom here, it downloaded a graph for me. I'm obviously using the Chrome browser. If you're using a different browser, it's going to work a little differently for you, but I like Chrome. All right, so it just downloaded it and it put it in my downloads folder. Therefore, when you guys submit this to me, you can just pull it out of the downloads folder and send it to me as an attachment, which is exactly what I want you to do. But when you send it to me as an attachment, you're going to find that there is a text box. Now, because I'm in the teacher version of Canvas, not the student version, you don't see the text box. But what's going to happen is when you click the button that says submit, it will give you a place where you can attach the file. And there will also be a text box. And what I want you to do is in the text box, I want you to tell me what is the equation that fits it the best. And I don't want you to give me the generic a squared root of x plus b. I want you to tell me what is the value of a that makes it fit the best, or what is the value of b that makes it fit the best. Or if it does turn out to be a straight line, I want you to tell me what is the m value that makes it fit the best, or the b value. Okay, and play around with a couple other functions too. Play around with logarithmic, play around with all the others, and just see which one works the best. Now, one last thing, or a couple last things before you go. One is, how do you know which equation is the best? Did your math teacher talk to you about this r squared number that you see up in the left here? Do you see how it went for my square root function, my r squared value is 0.9987. For my linear function, the r squared value is 0.98. Does anybody know about r squared and what that means? Oh my goodness, you guys are, okay, no, okay. Well, yeah, you're learning a lot today. All right, I'm not going to go into the detail of how r squared is calculated. When you take the statistics class, which I hope everybody will take, that's when you will learn how it works. But basically, it's a number that the closer to 1 it is, the better the fit is. So if it fit absolutely perfectly, the r squared value would be 1. But if you're using data that you've gained through some experimental technique, then it's never going to be 1, but it will be really close. So you can see here with our square root function, we got an r squared of 0.9987. That is really, really, really close to 1. Now the linear function wasn't bad either. 0.98, that's pretty close to 1 too. But 0.9987 is better. So clearly I can see that the square root function is doing a better job of fitting the data. And I don't even need to look at the graph. I mean, if you guys look at the graph, it's obvious from the graph which one it is. But even without looking at the graph, if you just look at this r squared value, you can see which one fits it the best. All right, I think that you guys are positioned well to where you can do tonight's homework. Before you log off, let me just ask, does anybody have questions about what we just did? Do you understand what the assignment is, and are you confident that you know how to do the assignment? All right, so here's what I want you to do. I want you to type into the chat box either yes or no. And once you've done that, you can then log out of Zoom and you can use the rest of the time here to work on the assignment. So yes is basically the equivalent of saying bye. If you have any questions, then type in no. And after everybody else has logged off, then you and I can talk one-on-one to clear up any questions that you might have. All right, you're welcome, Julia. So far, all I'm seeing are yeses, so you guys can start logging off. Ah, right, Zane. Okay, so fine. I'm glad to see that you were honest there, Zane. What could I do to help you understand this better?
So in the pendulum lab, there is is a period timer. Can we use that instead?
That would be cheating. That would be too easy. Where's the fun in that? No,
Mhm.
if you use the period timer, what's going to happen is you're going to get the same number every time, which is great, but it doesn't really represent reality. I want you to have an experience of doing a real life lab where you don't get the same answer every time. I wish you would have said something while everybody else was online, because other people might have had that exact same question.
Oh, okay. Thank
Any
you,
other
Mr.
questions?
Hendricks. Nope.
That's it? Okay, great.
Bye.
All right, I will see you later then.